Batuk and good afternoon. Okay, so for our chapter 5 topic, we will do it on 9th. Okay, so for our subject aerospace motion modeling, chapter 5, design experiment and design of experiment DOE. Okay, this is what we'll cover in this chapter, which is introduction of DOE, type of experimental design, full factorial, fraction factorial, and DO selection. The introduction of DOE. So design of experiments, for example, you have to study a performance of system in respect to particular parameter. In your system, you have routine algorithm of magnet, whereas your parameter, your number of nodes, which is n. For example, your number of nodes here, you have 10, 20, 50, 100, 1000, 10,000, and the rest. And you have another parameter which is mobility m, which is how long it will take, maybe take 1 meter per second, 3 meter per second, 5 meter per second, 10 meter per second. And the packet size, for example, P, you have 64 bytes, 456 bytes, 512 bytes, 1024 bytes. And number of parameter flow, which is F, you have 1, 3, 5, 7. So in terms of parameter space that you will do based on all the parameter and number of nodes, mobility times packet times times a number of parallel flows. So total out you will get 480. But in order to do experiment, you need to replicate it. So the replication at least minimum of 10, or it's better to have more, which is 30. So you will have about 4,800 to 14,400 simulation. The big question marks is how to perform the experiment to understand the effects of the parameter. In order to solve this issue, design of experiment is the solutions. So whereas the goal is to obtain maximum information with the minimum number of experiments. You have a lot of parameter, you have a lot of data, you have a lot of interaction data. So how you want to minimize it, you need to use the DOE, which is the maximum informations that you have with a minimum number of experiments. Okay, this is a terminology that you will face. One is the response variable, whereas the outcome of an experiment. So what is your outcome? Okay, the result outcome. Factor. What is the factor? Each variable that affects the response variables and has several alternatives. What is the factor of effects? Remember the introduction of DOE. So the factor will affect on the response and the rest. That is the level, which is the value that factor can be assumed. So you have a factor, how many, the level 1, 2, 3, or how many level. The primary factor, the factor whose effect needs to be quantified. Okay, secondary factor is factor that impact the performance, but whose impact are not interested in quantifying. Okay. Third is replications. So the repetitions of the experiment of sum of experiments, experimental units, any entity that is used for the experiment, interactions. Okay. For example, two factor A and B interact if the effect of one depends on another level. So interaction between two factors. So the first example shows there is no interaction. If you can see here, you have A1, A2, B1, B2. So the interaction of both is there is no interactions. So it's directly. So it's like a straight line or parallel. But the below shows the interactions, whereas the graph of the first one and the second one have a different results. So means it will interact between A and also B. A2 and B1, B2 and B1. So this one is more on parallel. So this is examples. So in terms of design is an experiment. Design consists of specifying the number of experiments, the factor level combination for each parameters, experiments, and number of replications. So in planning experiments, you have to decide before you start the experiment, you decide what is the measure to make the response. What do you want to see? What is the measure? If you remember, for example, you want to measure temperature, you want to measure pressure, you want to measure velocity. So you need to define. Second is what is the condition of the study. For example, in terms of temperature, temperature, you have ATM, atmospherics. So maybe outer space, what is the effects and the rest. Okay, in terms of velocities, for example, okay, in terms of velocity, for example, what is your conditions? Okay, maybe a laminar, turbulence, flow, okay, and the rest. Okay, so the third one is what experimental material to use to be units. The units, for example, pressure, Pascal, and the rest. So another example is to measure good put and overhead of routing protocol, network with nodes and chains, routing protocol type of nodes and link and traffics. This is example of designs. The type of experimental designs. First, simple design. Simple design is start with configurations and vary one factor at a time, given k factor and I factor having n level. So the requirement number experiment is n. How many number factor n is equal to 1 plus from I, for example, 1 to k, where is your ni minus 1. Okay, for us, this is the formula of simple design. So for examples, you have k equal to 3. So your n1 is 3, n2 is 4, n3 is 2. So what is your total number of n? So first is 1 is 1, plus summation of each one, n minus 1. The first n is 3, 3 minus 3 minus 2, so you become 1, sorry, 3 minus 1 become 2, 4 minus 1 become 3, okay, 2 minus 1 become 1. So total up you will get 7. Okay, so this is a simple design requirement in order for you how many tests that you want to try. Second is full factorial method. Full factorial method, what is full factorial method? Experiment looks completely at all factor include the experimentation. Whereas in the full factorial method, all the possible combination that are associated with the factor and their level are studied. So the effect of main factor and all interaction between a factor are measurable. So you have a factor. So what is the effects? Okay, so you will measure. Then if you use more than 2 levels of each factor, we can also study whether the effect of response is linear or if there is a curvature in the experimental region, each of the factor of interaction. So you want to see the interaction. Third is the full factorial experiments can require many experiment runs if many factors have many level of investigations. Okay, for example, full factor of design, use all possibility combination and all level of factor. So given k factor and I factor having n, so the formula of full factor is something like this. You are considering all. For example, your k is 3, you have n1, n2, which is 4, and 3, which is 3. So what you need to consider for n is you multiply every of the factorial. So you have 3 times 4 times you total up, you have 24 of experiment that you need to have. Okay. So this is full factor. You need to consider all. Consider all. Okay. Another one is fractional factorial methods. Fractional factorial suits more factor with fewer runs. So you have more factor, but how we want to do it in the fewer runs. So using fractional factorial involve making major assumptions that higher order interaction, those between 3 or more factor, are not significant. Okay, fractional factorial design are derived from full factorial matrix by substituting higher order with a new factor. So it to increase the efficiency of experimentation, factorial given up some power analyze the effect of response. Fractional factorials will still look at the main factor effect, but they lead to the comprises when looking into interaction effects. So this is called confounding. Okay, this is example fractional factorial designs. So for example, when you have full factorial design results in a huge number of experiments, it may not be possible to run all. Okay. Okay, so for example, use subset. You need to use subset level of factor and the possible combination of these. So given k factor and the I factor of n level, and select subset of the level where is your m is lesser than your n. So you need to select your m is lesser than n. So that's required number of experiment. Okay. So for example, you have k 3, you have n1 3, n2 4, and 3 2, but use m1, but we need to use the m which is lower, so we take it m1 as a 2, m2 as a 2, m3 as a 1, so n2 times 2 times 1, so it become 4. So you only have 4 number of experiment need to conduct. So this is fractional factorial design. So type of experiment here, first simple design. Okay, as mentioned, you have 3 and 3 to 4, so total up you will get 7 just now. Okay, this is an error. So full factorial you need to do it 24, and fractional factorial design by using subsets you only have to do it 4. Okay, so this is 2k factorial designs. Okay. Okay, what is 2 power of k factorial design? A 2 power of k factorial design is used to determine the effect of k factor. Each factor have 2 levels. So you have a 2 factor, then you have a 2 levels of factor. So the advantage is easy to be analyzed, help to identify the important factor, reduce the number of factor. Okay, often effects of factor in unidirectional. Okay, example, performance increase or decrease, and begin by experimenting at the minimum and maximum level of factors for the 2 levels. Okay, this is example of 2k factor. So you have 2k, you have 2 factorial with the 2 levels. So you have 2 factorial, for example, a1, a2 is 2 level of b1 and b2. Okay. So the 2k factorial design example, for example, to study the impact of memory cache on performance of workstations. So you have memory size 2 levels, cache size 2 levels, performance of the workstation, and regression. If you can see on here, you have a memory, for example, 4 megabyte, 60 megabyte, cache of 1, you have -1, -1, and the rest. So total up for XA, you have from 1 to -1 if possible for if M 4 megabyte memory and 60 megabyte. For XB is 1 to -1 if 1 cache and also 2 KB. Okay, so how it works is, example, for example, regressions. This is a formula of regression. You have Y equal to Q nodes, okay, plus QA times XA, QB times XB, QAB times XAB. So, for example, you have 4 experimental data. Okay, 1, 1, 2, 3, 4. So your A is -1, 1, -1, 1. B is -1, -1, 1, 1. This is your Y2 and until 4. And AB is a time from A to B. A times B, -1 become 1. 1 times -1 become negative. This one become negative. This one become 1. For example, this is your experimental data. So how to solve this one? You need to find each of the Y. So what is Y1? Y1 is Q nodes minus QA, okay, Q nodes minus QA times XA. So yeah, X is -1, that's why it become negative here. Okay, your minus QB times XB. So QB times XB, your XB is negative, this one become negative. So the third one is QAB times XAB. So QAB times XAB is 1, so that's why it become positive. So we start with Q2. Okay, Y2 is Q nodes plus QA times XA. So you will get 1 because this is positive. This is positive. Then B become negative. This is negative. QAB become negative. You become negative. Then Y3 also Q node plus -1 because this is negative. Then it become positive here because of this positive. And this one become negative. This is negative. And the rest. Okay, the moment you have this one, So you need to solve the QI. How to solve this QI? You need to use the, you need to take the mean. So y1 plus y2 plus y3 by y4 divided by 4. So you have these calculations. So you calculate everything for Q nodes. So you get the Q nodes. Then QA, everything just now, okay, you times this y, you will get QA divided by 4, you get QA, okay, then QB, and the rest. At the end, your y will be this one, y equal to 40 plus 2xa plus 10xb plus 10xb. Okay, okay, this is example for K2 for sine table method. Okay. Okay, for sine table methods, the sine table content effect of factor. Okay, you have, for example, I, A, AB, B, AB, and Y. So in this case, for example, you have Y is 15, 45, 25, 75. So your I is 1, 1, 1, 1. So your summation of I is I times Y equal to 160. How you want to do it? 15, I times 15 become 15 plus 45 plus 25 plus 75, you will get 160. And this 160, you need to divide it by 4 because you have 1, 2, 3, and 4. That's why it become 40. So same like this become negative 15 because negative 1 times 15. Okay. Then plus 45 plus minus 25 plus 75, we get 80, divided by 4, we will get 20. So same like this, negative 15 minus 45 plus 25 plus 75, we get 40, divided by 4, you will get 10. And AB, you will get 15 minus 45 minus 25 and plus 75, you will get 20, divided by 4, you get 5. So total up, you have total divided by 4. This is your K2 result for sine tables. Okay, so the moment you have that, we need to find the allocation of variations. So determine the important factor. So this is a calculate the variance. How to calculate variance? This is a formula. S square summation of y minus mean square divided by 2 square minus 1. So this one is sum square total, SST, total variations. So this is the formula. Okay. Then the third one, for 2 power of 2 design, the variation is given by SST is equal to 2 power of 2, 2 power of 2, QA2 plus 2 power of 2 QB2 and Q power of 2 of QAB2. So for example, for the allocations just now, so this is the formula. So what happened is SSA, the first one, okay, will explain the factor of A. The second one will explain the factor of B, and the third one will explain the factor of C. So in order to calculate the fraction of variation explain A, so SSA just now divided by SST. So SST, you need to calculate SST for each one. Okay, and SSA just now, oh sorry, this one, SSA divided by SST, SSB divided by SST, and SAB divided by SST, you will get the fraction. Okay, so this is the 2k factorial designs, the general case. In the general case, there are k factor. Each factor has 2 levels. So with a total of 2k experiments are required. Analysis produce 2k effects. So k remain effects or 2-factor interaction or 3-factor interaction. So we can see the sign table here. For example, you have k equal to 3. Okay, so this is your table that k equal to 3. So you will have A1, A2, A3, A times 1, A1A, A13, A times A3, A23, and A times 3, all these 3. So you will have 1, 2, 3 until 8. Okay? Then for the sign tables, same 2 power of k. Okay, so this is a factorial design with replications. What is factorial design with replication? Problem with 2k factorial design is that it does not provide estimation as experimental error just now. So it's no repetitions. So just now there is no repetitions. So in order, the solution is repeat experiment for R time and replication. Okay. So if each of the 2k experiment is repeated for R times, 2k R factors design will be replications. So this is the extended models, for example, just now, then times the experimental error. And you see the same method is used, except why the mean replication is used. Okay, same the method. For example, the calculation of I is the same. Okay, 15s, all positive, times 48 times 24 times 77, you will get 104 divided, this divided by 4. You have 1, 2, 3, and 4. Divided by 4, you will get 41. So same like this, negative 15 times 48 plus 48 minus 24 plus 74, you get 86. Okay, divided by 4, you will get 21.5. B, negative 15. Okay, this one times this one. Okay, negative 15 minus 48 plus 24 plus 77, you get this one. Divided by 4, you get this one. Then you had A, B for this one, you get 20 divided by 5. Divided by 4, divided by 5. So, but why the calculation are a little bit different, I will show you after this. So this one, you calculate everything. So this is in terms of replications. How many replications? Okay. The effects, this is the effects of that A, B, C, A, I, A, B, A, B. The estimation response is 15, 48, 24, 75. This will be based on the Y. Okay. Then major response. The major response, okay, is 15, 18, 20, 12. So how we get this one 15? Because we take the mean. Okay, 15 plus 18 plus 12 divided by how many we have? Divided by 3. So you will get 15 here. So 45 plus 48 plus 51 divided by 3, you will get this answer, 48. Okay. 25 plus 28 plus 19 divided by 3, you will get 24, and 75 plus 75 plus 81 divided by 3 equal to 74. Okay, this is in terms of how the estimation response of Y, how to calculate response of Y. So what is the error? The error is, experimental error is given that Y minus Y mean. So in this case, you have 15 here. 15 minus 15 becomes 0. Okay. 18 minus 15 become 3. Negative 12 minus 15 become negative 3. Same like this. 45 minus 45, this one for the one, 45 minus 48, you get 3. Okay, 48 minus 48, get 0. And you want 51 minus 48, you get 3. So this is your how to calculate the error of A11, A12, and A13. The sum of square SSE and the standard deviation error is this formula. So SSE divided by square root of 2R minus 1. So the SST, sum of square root SST, so it's a summation of Yij minus square. So SST can be divided into 2 parts. First is the summation of SSA, summation of SSB, summation of SSAB, and summation of error, SSE. Okay, so you have summation of SSE based on these equations, the confidence interval by using these equations. Okay, now it's 2k minus 1 fractional factorial design. Okay, 2k minus p fractional factorial designs is when the number of factors is larger. Okay, you have factors larger. A full factorial design requires a large number of experiments. So in that case, fraction factorial design can be used. Okay, so you remember use the subset. So it's require fewer experiments. So this is the main objective is to require fewer experiments. So where k minus l require half of experiment as full factorial. So it's half from the full factorial. Okay. Preparing the sign table, choose k minus p factor and prepare a complete sign table. The sign table with k minus p in terms of row, in terms of column. You have row and column. The first column will be marked as I and consists of IS. The next KP column will be marked as k minus p factor that were chosen. The remaining column are simply products of this factor. So you can see here, for example, you have some example k minus 7 equal to 7, whereas your p equal to 4. So automatically we know that k 2 k minus p, whereas become 2 7 minus 4 become 2 power of 3. So in terms of row, you have 2 power of 3 row, and column also you have 2 power of 3. So automatically we know that k minus 4 become 2 power of 3. So I have 1, 2, 3 here. And ff times f1 become f12, f13, f23. So automatically you have 1, 2, 3, 4, 5, 6, 7, and I is 8. 8 plus 2 times power of 8 equal to 8n. Okay, so that's in terms of column. In terms of row also you have the same one. So you should have 2 power of 8. So become 1, 2, 3, 4, 5, 6, 7, 8. So this is your I. For example, I start with positive, positive, positive. Everything will be positive. Okay. Then F1 positive, negative, positive, negative, positive. Second is negative, negative, positive, positive, negative, negative, and the rest is more on completed table. Okay. In terms of 2kp fraction factorial design, we call it as a confounding. With the fractional design, some of the effect cannot be determined. Only combined effect of several factors and can be computed. A fraction is not a unix. So design solution, the solution of design is measured by the order of effects that are confounded. The order of effect is the number of factors included in this. There is, for example, you have I equal ABC. You have an order of 3, the evolution of R3. If your A, B, C, D, you have a 4, revolution for R4. So please remember, a design of higher resolution consider a better design. So you can see this is a better design than this one. Okay. So as summary, what we learn here is we learn about design of experiment provide method for plan. Okay, the goal obtain maximum information with minimum experiment, basic technique factorial designs, factorial with application, and factorial designs. Fraction factorial designs. Okay.